scientists to this short video. In this video, we're going to solve problem 15 from chapter 4. When we go to solve this problem, I see that there are two ways that we can approach this problem. The first, I'm going to use integral calculus to solve for the velocity and position functions respectively, and then solve the questions at hand. The other method is to use our knowledge of kinematics. I noticed that the acceleration is constant both in the horizontal and vertical direction, so I'm allowed to use those one-dimensional motion equations for constant acceleration. So that's another method that I could have used. You'll see which one that you like best, and that's the way that I think you should approach this problem. With that, let's get started. In problem 15, you can see that they've given us a particle that has an acceleration. The acceleration is both in the negative x direction as well as the negative y direction. This particle has initial velocity of 3 meters per second in the positive x direction. So I know this particle is going to move in the positive direction, slowing down, stopping, and then turn around and move back in the negative direction, speeding up. However, it's also going to start from rest vertically and accelerate downward, getting faster and faster in the downward direction the entire time. In this first method, I'm going to use calculus to determine the velocity and position functions. So I have an acceleration function. I know that I can take the integral to get a velocity function. When I integrate -1 with respect to time, I get -1t plus a constant. And we know that that constant of integration is 3, my initial velocity. And when I integrate -0.5, I get -0.5t plus c, where c is my initial velocity in the vertical direction, but that's 0. Now I can integrate for the position function, and I know that I want to integrate each term independently. When I integrate my x direction, I get -0.5t squared plus 3t plus my initial position, which in this problem was given to me as 0. And I get half of a half, which is a quarter, or -0.25 j hat. This problem asked me to find the maximum horizontal position. So I know that that maximum is going to be obtained when the horizontal velocity is equal to 0, because that's when the particle is going to have stopped and turned back around. So I set the I hat component of velocity function to be 0. So now I know the time that it takes the particle to reach its maximum horizontal position. And the problem wanted me to determine the velocity at that moment. So I just need to plug that time, 3 seconds, into my velocity function. And I see that the particle has stopped moving side to side and is moving completely downward with a speed of 1.5 meters per second, negative, because it's in the negative j hat direction. The problem also wanted me to find the position of the particle, so I'm just going to go ahead and plug in that 3 seconds into my position function. And there I've got my position function. The other way to approach this problem is to use the kinematics equation. I recognize that the acceleration is constant both in the horizontal and vertical dimensions, so I can create my 2-dimensional data chart, filling in the given information that I know. This problem specifies that they want to find the velocity in the y direction and the position when the velocity in the x direction is 0, when it reaches its maximum position. So I know I can go ahead and set that constraint. I now have 3 independent pieces of information, and I guarantee you that I can solve this problem. You can see there that I've solved that out algebraically, but it just makes sense. We know that the acceleration is the change in velocity. If my particle starts with a velocity of 3 meters per second, and I take away 1 meter per second every second, it's going to be 3 seconds until it stops. Here's just the algebra that backs up my intuitive knowledge that it's going to take 3 seconds for this particle to stop. Now that I know the time it takes to stop, I can go ahead and solve for the displacement. I just realized, you saw me hesitate there. I realized I wouldn't have even done, like, I needed the time to do the y dimension, but I wouldn't use that to find the displacement because there's a better equation for me to use. Final squared is equal to initial squared plus 2ax will give me what I want without the dependency on time. And that way, if I screwed up getting my 3, I'm not going to screw up getting my position in the x direction. So it's a little bit better of a choice, but I need to find that 3 to solve the y side anyway. So the 6 of one, half dozen the other. Do whatever you want. 0. Yay, it works the same as what I got in the other way of solving this problem, so I'm happy. And now I want to look in the y dimension. So I've solved for part B, position in the vertical and horizontal dimensions, but I didn't get the speed in the vertical dimension yet, so I'd have to go back up and do that. And again, I got the velocity component in the y to be negative 1.5, so it's moving with a speed of 1.5 meters per second in the downward direction, which corresponds to what we saw with the other method. So there you have it. In this video, we saw there were two different methods that we could use to solve problem 15 from chapter 4. We could have used integral calculus, or we could have used our constant acceleration equations. That's all for this video. We'll see you in the next one.